Welcome to the fascinating chemistry of two transformative processes that have shaped human civilization for millennia. Fermentation, an ancient metabolic pathway, converts sugars into acids, gases, or alcohol using microorganisms like yeast and bacteria. It gives us bread, beer, wine, yogurt, and cheese. Saponification, the chemical reaction that produces soap, involves the hydrolysis of esters, specifically triglycerides, using a strong base to yield glycerol and fatty acid salts. Both processes are rooted in organic chemistry and share the theme of molecular transformation. In this presentation, we will explore the detailed mechanisms, equations, applications, and quantitative aspects of fermentation and saponification. You will learn the glycolysis pathway, the role of enzymes, the ester hydrolysis mechanism, and how to calculate yields. Fermentation is an anaerobic metabolic process in which microorganisms such as yeast and bacteria convert carbohydrates like glucose into simpler compounds, releasing energy without the use of oxygen. It is an ancient biotechnology dating back thousands of years, used by early civilizations to preserve food and create alcoholic beverages. The process begins with glycolysis, where one molecule of glucose is broken down into two molecules of pyruvate, producing a net gain of 2 ATP and 2 NADH. Under anaerobic conditions, the pyruvate is further converted into fermentation end products to regenerate NAD+, which is essential for glycolysis to continue. The two most common types are alcoholic fermentation, performed by yeast, and lactic acid fermentation, performed by bacteria in muscle cells. Alcoholic fermentation is performed primarily by Saccharomyces cerevisiae, baker's and brewer's yeast. After glycolysis produces pyruvate, the enzyme pyruvate decarboxylase removes a carboxyl group from pyruvate, releasing carbon dioxide and forming acetaldehyde. This is a key step that distinguishes alcoholic from lactic acid fermentation. The second step involves the enzyme alcohol dehydrogenase, which reduces acetaldehyde to ethanol using NADH as the reducing agent. This regenerates NAD+, allowing glycolysis to continue producing ATP. The overall reaction converts one glucose molecule into two molecules of ethanol and two molecules of carbon dioxide. The CO2 produced is responsible for the rising of bread and the carbonation in beer and sparkling wines. Lactic acid fermentation occurs in certain bacteria such as lactobacillus and in animal muscle cells during intense exercise when oxygen supply is limited. In this process, pyruvate produced from glycolysis is directly reduced to lactic acid by the enzyme lactate dehydrogenase using NADH. This single-step conversion regenerates NAD+ without releasing carbon dioxide. The product, lactic acid, gives yogurt and sourdough their characteristic tangy flavor and acts as a natural preservative. In human muscles, when oxygen demand exceeds supply during strenuous activity, lactic acid accumulates, causing the familiar burning sensation and muscle fatigue. The liver later converts lactate back to pyruvate through the Cori cycle when oxygen becomes available. Fermentation is one of the most economically important biotechnological processes. The food industry relies on it for producing alcoholic beverages, bread, yogurt, cheese, vinegar, soy sauce, and fermented vegetables. In biofuel production, large-scale fermentation of corn, sugarcane, and cellulosic biomass produces ethanol as a renewable fuel additive. The pharmaceutical industry uses fermentation to produce antibiotics like penicillin, vitamins, amino acids, and recombinant proteins through genetically engineered microorganisms. Industrial fermentation is carried out in bioreactors with carefully controlled conditions including temperature, pH, nutrient concentration, and oxygen levels. The global fermentation market exceeds $200 billion annually, spanning food, fuel, pharmaceutical, and chemical sectors. Saponification is the chemical reaction between a fat or oil, a triglyceride, and a strong base, typically sodium hydroxide NaOH or potassium hydroxide KOH, producing glycerol and fatty acid salts, which are soaps. The word itself comes from Latin sapo, meaning soap. This reaction is a specific type of ester hydrolysis, where the ester bonds in triglycerides are cleaved by the base. Triglycerides are esters formed from glycerol and 3 fatty acid molecules. When treated with a strong base, each ester bond is broken, releasing 1 fatty acid molecule that is immediately converted to its carboxylate salt, the soap molecule. Saponification has been practiced for thousands of years, traditionally by mixing animal fats with wood ash, which contains potassium carbonate, a base. The reaction is exothermic and produces heat. The type of fatty acids in the fat determines the properties of the resulting soap, including hardness, lathering ability, and cleansing power. The saponification mechanism proceeds through a nucleophilic acyl substitution pathway. The hydroxide ion from the base acts as a nucleophile, attacking the electrophilic carbonyl carbon of the ester group in the triglyceride. This forms a tetrahedral intermediate. The intermediate collapses, expelling an alkoxide ion derived from glycerol. The alkoxide quickly abstracts a proton from water, regenerating the hydroxide catalyst and releasing the fatty acid salt. This process repeats 3 times for each triglyceride molecule, once for each ester bond. The reaction is irreversible because the carboxylate product is stabilized by resonance and cannot reform the ester. The saponification number is defined as the milligrams of KOH required to saponify 1 gram of fat, and it indicates the average molecular weight of the fatty acids present. Soap making involves mixing fats or oils with a calculated amount of alkali. Traditional soaps use sodium hydroxide for solid bar soaps and potassium hydroxide for liquid soaps. The choice of fat determines soap properties. Coconut oil produces a hard bar with excellent lather, olive oil gives a mild, gentle soap, and palm oil contributes hardness. Superfatting, adding extra fat beyond what the alkali can saponify, creates a moisturizing soap that is milder on skin. The cleansing action of soap relies on its amphiphilic nature. The long hydrocarbon tail is hydrophobic and dissolves grease, while the ionic carboxylate head is hydrophilic and remains in water, forming micelles that trap and remove dirt. Modern detergents are synthetic surfactants developed during World War I due to fat shortages. Quiz question 1. Which of the following is the main purpose of fermentation? Option A. Produce oxygen for respiration. Option B. Regenerate NAD+ to sustain glycolysis. Option C. Synthesize proteins from amino acids. Option D. Break down fatty acids for energy. Take a moment to think about your answer. The correct answer is B. Regenerate NAD+ to sustain glycolysis. The primary purpose of fermentation is to regenerate NAD+ from NADH so that glycolysis can continue producing ATP in the absence of oxygen. Quiz question 2. What is the key difference between alcoholic and lactic acid fermentation? Option A. Alcoholic uses bacteria, lactic uses yeast. Option B. Alcoholic releases CO2, lactic acid does not. Option C. Lactic acid produces ethanol, alcoholic produces lactate. Option D. There is no difference. Think carefully about the 2 pathways. The correct answer is B. Alcoholic fermentation releases CO2, lactic acid fermentation does not. In alcoholic fermentation, Pyruvate decarboxylase removes CO2 from pyruvate to form acetaldehyde. In lactic acid fermentation, pyruvate is directly reduced to lactate without releasing CO2. Quiz question 3. In saponification, what acts as the nucleophile that attacks the ester carbonyl? Option A, water molecule. Option B, hydroxide ion OH-. Option C, carboxylate ion. Option D, the glycerol backbone. Remember the mechanism of base-catalyzed ester hydrolysis. The correct answer is B. The hydroxide ion OH- from the strong base acts as the nucleophile. It attacks the electrophilic carbonyl carbon of the ester, forming a tetrahedral intermediate that collapses to release the fatty acid salt and glycerol. Quiz question 4. Why is soap able to dissolve grease in water? Option A. It reacts chemically with grease. Option B. It is amphiphilic with a hydrophobic tail and hydrophilic head. Option C. It raises the water temperature. Option D. It breaks grease into smaller molecules. Think about the molecular structure of soap. The correct answer is B. Soap molecules are amphiphilic. The long hydrocarbon tail dissolves in grease, while the ionic carboxylate head stays in water. This allows soap to form micelles that trap grease particles and wash them away. Quiz question 5. The overall equation for alcoholic fermentation of one glucose molecule produces what? Option A, 1 ethanol and 1 CO2. Option B, 2 ethanol and 2 CO2. Option C, 2 lactic acid and 2 CO2. Option D, 3 ethanol and 3 CO2. Use the balanced equation for alcoholic fermentation. The correct answer is B. One glucose molecule, C6H12O6, is converted to 2 ethanol molecules, C2H5OH, and 2 carbon dioxide molecules, CO2. This is the overall balanced equation for alcoholic fermentation by yeast. Problem 1. Calculate the theoretical mass of ethanol produced from the fermentation of 500 grams of glucose, assuming 100% efficiency. The balanced equation is C6H12O6 yields 2C2H5OH plus 2CO2. Step 1. Calculate the molar mass of glucose. 6 carbons times 12 plus 12 hydrogens times 1 plus 6 oxygens times 16 equals 72 plus 12 plus 96, which is 180 grams per mole. Step 2. Calculate moles of glucose. 500 grams divided by 180 grams per mole equals 2.78 moles. Step 3. Use the stoichiometric ratio from the balanced equation. The mole ratio of glucose to ethanol is 1 to 2. So moles of ethanol equals 2 times 2.78 equals 5.56 moles. Step 4. Calculate the mass of ethanol. The molar mass of ethanol is 46 grams per mole. Mass equals mig del 56. Moles times 46 grams per mole. The answer is 256 grams of ethanol. Problem 2. What volume of CO2 gas at STP is produced when 1 kilogram of glucose undergoes alcoholic fermentation? Step 1. Convert mass to moles of glucose. 1,000 grams divided by 180 grams per mole equals 5.56 moles. Step 2. Find moles of CO2 from stoichiometry. The mole ratio of glucose to CO2 is 1 to 2. So moles of CO2 equals 2 times 5.56 equals 11.12 moles. Step 3. Convert moles to volume at STP. At STP, 1 mole of any gas occupies 22.4 liters. Volume equals 11.12 moles times 22.4 liters per mole. The answer is 249 liters of CO2 at STP. 1 kilogram of glucose yields about 250 liters of CO2 gas. Problem 3. A sample of glycerol tripalmitate, also called tripalmitin, weighing 250 grams is saponified with excess NaOH. Calculate the mass of sodium palmitate soap produced. Step 1. Calculate moles of tripalmitin. 250 grams divided by 807 grams per mole equals 0.310 moles. Step 2. Use the mole ratio from the saponification equation. 1 mole of fat produces 3 moles of soap. So moles of soap equals 3 times 0.310 equals 0.930 moles. Step 3. Calculate the mass of soap produced. The molar mass of sodium palmitate is 278 grams per mole. Mass equal 0.930 mol estimas 278 grams per mole. The answer is 258 grams of soap. The saponification of 250 grams of fat yields about 258 grams of soap. Problem 4. A 2-gram sample of coconut oil requires 35 milliliters of 0.50 molar KOH for complete saponification. Calculate the saponification number and the average molar mass of the oil. Step 1. Calculate moles of KO used. Moles equals molarity times volume. 0 horas y 50 minutos moles per liter times 003 5 liters equals 00. 175 moles. Step 2. Calculate mass of KOH. Mass equals 0.0175 moles times 56.1 grams per mole equals 0.982 grams, which is 982 milligrams. Step 3. Calculate the saponification number. 982 milligrams of KOH divided by 2 grams of oil equals 491 milligrams KOH per gram of oil. Step 4. Calculate the average molar mass of the oil. Mass equals 56.1 times 3 times 1000 divided by 491. The answer is 343 grams per mole. The saponification number is 491. Problem 5. The fermentation of glucose releases 235 kilojoules per mole of energy. The balanced equation is C6H12O6 yields 2C2H5OH plus 2CO2 with a delta G of minus 235 kilojoules per mole. How much energy is released when 2.5 kilograms of glucose is fermented? Step 1. Calculate moles of glucose. 2,500 grams divided by 180 grams per mole equals 13.89 moles. Step 2. The energy released per mole of glucose is 235 kilojoules, since a negative delta G means exothermic. Step 3. Total energy released equals 13.89 moles times 235 kilojoules per mole. The answer is 3,264 kilojoules released. This is enough energy to heat 10 liters of water from 20 degrees to 98 degrees Celsius. Let us review the essential concepts. Fermentation is an anaerobic process that converts glucose to ethanol and carbon dioxide, or to lactate, regenerating NAD+ to sustain glycolysis. The key enzymes are pyruvate decarboxylase and alcohol dehydrogenase in alcoholic fermentation, and lactate dehydrogenase in lactic acid fermentation. This process is fundamental